We've known for nearly 100 years that vitamin C prevents scurvy, so why can't I seem to get a straight once and for all answer on whether chocolate lowers my risk of cancer? Or what about coffee, or soy, or even kale? These are fair questions. Maybe you've asked one of them before yourself. Why does science seem to be so sure about some things, but not others? Hi, I'm Hank Green, and this is Crash Course Scientific Thinking. I don't care if it's good for me. Today, we are going to talk about scientific consensus, the point when an idea with a strong base of evidence gains broad acceptance by scientific experts. It's how science moves forward. Consensus is way more than an opinion or a vibe, and also a very different thing from just letting your Gen Z colleague rename the group chat Meatball Zone because it wasn't worth the fight, which is a real thing that happened to me. Scientific consensus happens only when a claim has been run through the gauntlet of skepticism. Scientists have conducted many studies. They have sifted through the evidence, argued with each other, tested an idea again and again with different techniques and approaches, scrutinized studies that others have done, and reached a point where the evidence backs one explanation as far more likely than any other. Consensus happens only after an idea has been poked and prodded and tested from many angles. And getting there isn't easy. Building a consensus takes a lot of time and effort. Think about atoms. Not those atoms, these atoms. But of course, I've never seen an atom before. Even the highest resolution picture any human has ever taken of them just kind of looks like blurry, out-of-focus blobs. But scientists agree that atoms exist and make up everything because they've worked for centuries collecting evidence and performing experiments to form a consensus around those tiny little building blocks. To learn more about this, let's get some sage advice.
What a fine day to learn about science, Hank, and puzzles.
Ooh, puzzles. I sense an analogy coming, Sage.
So, the scientific process for building consensus is kind of like putting together a jigsaw puzzle, but without seeing the picture on the box. In the case of atomic theory, it started thousands of years ago as this idea that everything in the universe was made of tiny, unseeable particles, what the ancient Greeks called atoms.
Clever name, I like it. Now, at first, it was more of a philosophical thought experiment before it was science, but then this guy, John Dalton, started thinking about it more scientifically.
Exactly. Dalton, who was a chemist in the early 1800s, started to apply that old philosophical idea to his research into chemical reactions. See, the existence of atoms helped explain certain patterns he was seeing in his work. He put the first puzzle pieces on the board. He said, here's the thing that could explain what matter is made up of.
It had explanatory power, the ability to explain a phenomenon through evidence, and that's one of the most important jobs of a scientific theory.
But it was still just a few pieces of the puzzle. He wasn't anywhere near seeing the whole picture or having scientific consensus. Flash forward to the end of the 19th century, and new experiments provided evidence for what scientists had long expected. There's something even tinier inside of atoms that's negatively charged. Electrons! That theory gained more and more support until we had more puzzle pieces and an even clearer picture of what an atom looks like.
And not long after that, the nucleus was discovered, but there were still big questions waiting to be answered, things that we did not understand well enough to agree on.
Exactly, like electrons are weird.
So weird.
And we can't say with absolute certainty where they'll be at any given moment. So in 1926, we started visualizing electrons as clouds of probability. Scientists agreed, based on all the available evidence, that the best we can say isn't where an electron is, but where it's most likely to be.
Being more precise about what we don't know actually makes the picture clearer.
And naming areas of certainty and uncertainty is what allowed scientists to come to a strong consensus around atomic theory. And that's today's sage advice.
So that's how science agrees about stuff. But why are there things science can't agree on, at least not fully? Like, how can there be consensus about stuff as tiny and practically invisible as atoms, but not about the food I put in my body? It can feel like there's a lot of mixed messages around food science, but there's actually quite a bit about basic nutrition that we do have consensus on. We know that vitamin C prevents scurvy, like I mentioned before, but also that vitamin D prevents rickets. We know that fiber is good for us, and too much saturated fat, salt, and sugar can be harmful to our health. But there can be areas of uncertainty within a broader scientific consensus, and that's actually where most modern-day science happens, in the nooks and crannies of what we don't know within the broader context of what we do know. Sometimes this means we're seeing details we didn't see before because we didn't have all the pieces. Other times it means that our idea of what the picture looks like has changed because we've got enough pieces to understand it more clearly. It's important to remember that debate may still happen about smaller details without disproving the main conclusion. That scientific debate is part of the process. It's how scientists refine a consensus. It's the same with the science of nutrition. There are some areas that are tricky to bring into perfect focus because they're tricky to measure. Like, say that I want to understand once and for all whether eating chocolate raises or lowers my risk of getting cancer. It wouldn't be impossible, but it would take a lot of large, high-quality studies and someone who cared enough to actually pay for them. And if the effect wasn't very large, it would be hard to spot it. Plus, it would still be a challenge to get strong evidence either way because there's so much we can't control for when studying people and food and health. Like, you can't really ethically design an experiment where a group of people are on a very specific diet for a very long time. And also think about all the different types of chocolate out there, not to mention all the other foods that people eat that could affect the results of a single study. On top of it all, things like exercise, genetics, and the environment around you all impact your health too. Forget comparing apples to oranges, even comparing apples to apples isn't easy. In other words, it's hard to gather enough evidence to push a consensus around chocolate's health benefits toward an agreement. So even though the consensus around basic nutrition hasn't changed much for decades, there's still a lot we don't know about the interaction between an individual's health and the food they eat. And that brings me to something I think can feel frustrating, but in science is very important. Scientists always hold open the possibility that, with new evidence, an explanation could shift or become more refined, just like how our model of the atom has. But it wouldn't happen overnight. It would take overwhelming evidence to shift a scientific consensus. Which is why consensus is so important. It's a way of saying, okay, scientists can agree that there will always be a degree of uncertainty in any theory. But with that caveat, they can agree on some things that are very, very likely to be excellent at explaining the world. So where do we, as consumers of science media, usually encounters scientific consensus? It's often in statements like 99% of scientists agree on something, like 99% of scientists agree that climate change is caused by human activities. Let's unpack what that means. First off, there's no real threshold for consensus. Even though we often say things like 99% of scientists, all that really tells us is that we have a strong consensus. But you could have a strong consensus with 95% or 83%. Overwhelming consensus of any degree means that a claim has cleared a very, very high bar. It's like we've got 3,000 pieces of this puzzle, and 2,996 are spelling out climate change is real, and we are causing it. It would not just be weird, but wildly unlikely to uncover evidence that overturns this fact. It would be as strange as learning that atoms aren't real. Now, does this mean that we know everything there is to know about climate change? No, there's still plenty of stuff for scientists to debate and discover. But they're working on the unsettled details within the broader scientific consensus. Scientists aren't debating if climate change will bring serious warming to the planet. They're debating things like the importance of peat bogs for carbon storage or how fast methane breaks down in the atmosphere. Science can tell us a lot about the world, from atoms to nutrition to climate change, but it can't tell us everything. That's just not how science works. Science is the process of becoming less wrong over time, of always being open to new evidence, but also recognizing when an idea is very good at explaining all of the weird phenomena of our world, has stood up to challenges from every angle, and is extremely unlikely to be wrong. Consensus is all the big stuff that scientists agree on. They understand atoms enough to know what their properties are, they understand nutrition enough to offer overarching health guidelines, and they understand climate change enough to know that we are causing it. But they still don't have a complete model of the atom. They still can't say in every case what chocolate will do to your body, and there's more to study about how humans are affecting the climate. At the end of the day, scientific consensus is what emerges when an idea has consistently explained the evidence, predicted outcomes, and stood up to challenge. It's the big stuff, the things that we keep seeing confirmed again and again. We know so much more about the world than we did even 100 years ago. Our knowledge continues to build and grow, and those puzzles are getting more complete and more detailed all the time. But science never stops pushing at those edges of what we don't know and asking questions about the stuff we do. In our next episode, we're going to take a deeper look at the ways you can fact-check the world around you. I'll see you then. This episode of Crash Course Scientific Thinking was produced in partnership with HHMI Biointeractive, bringing real science stories to thousands of high school and undergrad life sciences classrooms. If you are a teacher, visit their website for resources that explore the topics we discussed in the video today. Thanks for watching this episode of Crash Course Scientific Thinking, which was filmed in Missoula, Montana, and was made with the help of all these nice people. If you want to help keep Crash Course free for everyone forever, you can check out our Patreon. There's a link in the description.